It's a very great privilege now to introduce the Revd Dr John Polkinghorne. He needs perhaps almost no introduction in science and religion areas, but he was formerly Professor of Mathematical Physics at Cambridge. He was ordained in the Church of England and then President of Queen's College, Cambridge. He is a Templeton Prize winner. I had the privilege of getting to know John when he came to visit Heidelberg when I was chaplain in the English-speaking church there. John was working with a colleague in the university, and I asked John to preach on Trinity Sunday, I remember, when the readings in the lectionary were about one verse each, with the grace at the end of 2 Corinthians, and I think it was the end of Matthew's Gospel and the Great Commission. And John delivered the most wonderful sermon, I have to say, and of course he has written about science and the Trinity, and he's also written a book related to the second lecture he'll give today, The God of Hope and the End of the World. So, John, over to you.
Thank you. I'm having back problems, and so I'm going to sit down if you'll excuse me. I lose in authority by sitting down, but I gain in comfort, and I think that's a worthwhile exchange. Well, what I'm going to try and do in this lecture is an exercise in a theology of nature. Let's say looking at the world, particularly as science explores the world, and seeking to understand it more fully and more deeply by looking at it from a theistic perspective, indeed from a Trinitarian perspective. So the claim is not, of course, that atheism is stupid or something like that, but that theism explains more and that Trinitarian theism explains yet more. A theology of nature is to be contrasted with a natural theology. Natural theology tries to move in the opposite direction, to say from nature to God. It can, of course, only be a limited form of exercise. First of all, it's insightful rather than demonstrative. There is no proof of God in that sense, and of course also because it only looks at limited evidence, the nature of the world, it only gives limited insight into the nature of God. God is the great mathematician or the cosmic architect. But I'm going to do it the other way around. So I'm going to start with the Trinitarian God and look at 6 different aspects of the world as science has explored it and discovered it, and suggest that those aspects of reality become more deeply intelligible, more coherent in our understanding of them if we look at them from a Trinitarian point of view. And the first 2 of them actually would also be possible components in an essay in natural theology. The first thing about the world is that it is intelligible, that science is possible, that we can understand it. Now, of course, obviously, evolutionary necessity explains a rough and ready understanding of the everyday world. If we couldn't figure out that it's a bad idea to step off the top of a high cliff, then we wouldn't be able to stay around for very long. We'd stay around a bit longer in this part of the world than most parts of the world, but not forever. That's one thing. That everyday experience is something quite different. And somebody like Isaac Newton comes along and sees that the same force that makes the higher cliff dangerous is also the force that holds the moon in its orbit around the Earth in its orbit around the Sun, to discover the mathematically beautiful universal law of inverse square law of gravity, and turns to that to explain the behavior of the whole solar system. Science is able to explore the world in a very deep way that seems to me to go far beyond anything that's necessary for everyday survival, or indeed could, in my view, be considered as a sort of happy accidental spin-off from everyday necessity. I mean, I was a quantum theorist. The quantum world is of course quite different from the everyday world. It's remote in terms of direct impact on the everyday world, though obviously we wouldn't be here without quantum theory, but apart from that, we're not aware of it directly, and it requires modes of thought that are quite different from our everyday modes. You know that quantum theory essentially is based on the superposition principle, the idea that in the quantum world you can add together things that common sense or logic would seem to tell you shouldn't be mixed together. Being here and being there. An electron can be in a state which is a mixture of those two. That's unpicturable. You explore it a little bit further, you find also it leads to a sort of probabilistic, fitful account of the subatomic world. Sometimes it will be found here, sometimes it will be found there. But we're able to understand that world in a very remarkable way. And the fact that science is possible is a non-trivial, as mathematicians say, a non-trivial fact about the world. And in fact, it's even stranger than that, because of course it is, in fundamental physics, it is mathematics, which it turns out to be the key that unlocks the secrets of the physical universe. It's an actual technique of discovery in my own subject, theoretical elementary particle physics, to look for theories which in their mathematical expression are characterized by beautiful equations. And we do that not as an act of aesthetic indulgence, but because it is a proven technique of discovery. Time and again, back in the 300-year history of modern physics, we found that it's only equations having that characteristic of mathematical beauty, which turn out to have a long-term fruitfulness, which also persuades us that they are describing the structure of the physical world. It's just possible that all of you will know about mathematical beauty. It's a rather austere form of aesthetic pleasure. It's concerned with things like economy and elegance, and what the mathematicians call being deep. That means you have a very simple-looking expression, which, as you explore it, turns out to have very remarkable and widespread consequences. All forms of beauty are hard to describe, but easier to recognize. And mathematicians can agree about what is mathematically beautiful. It is a real property, I think, of the world. And it turns out that's the way physics is. I mean, the greatest theoretical physicist I've known personally, I think, is Paul Dirac, who, of course, was the Lucasian professor here in Cambridge for more than 30 years, one of the founding figures of quantum theory. And Dirac once said, it is more important to have beauty in your equations than to have the fit experiment. So that. Now, of course, he didn't mean by that empirical adequacy was something you could dispense with. I mean, no scientist could possibly mean that. But what Dirac meant was this. Suppose you have your new theory. Suppose your equations don't seem at first sight to fit experiment. Well, that, of course, is a setback, but it's not necessarily absolutely fatal. Almost certainly, you'll have had to solve the equations in some sort of approximation. And maybe you made the wrong approximation. Or, of course, it's just possible that the experiments might be wrong. We certainly know that happened more than once in physics. So at least there was some sort of residual hope that all might be well in the end. But if your equations were unbelievable, there was no hope. They couldn't possibly be right, because the whole history of physics was against you. Dirac made his own very great discoveries precisely through a lifelong and highly successful quest for mathematical beauty. And he once said it was a very profitable religion to espouse. Now, I think he said that ironically he was not a religious man. But I think that the fact that mathematics is the key to unlocking the secrets of the physical world is something that we need to try and understand. It's a non-trivial fact, again, about the world. In fact, Dirac had a brother-in-law, Eugene Wigner, who also won a Nobel Prize for physics. And Wigner once said, why is mathematics so unreasonably effective? Why can we use it in this way? Why does the reason within, in other words, the mathematical thoughts of our study, mathematical thoughts of our minds, why does it fit the reason without the structure of the world around us? What connects the two together? It seems quite separate from each other. We've had mathematics, mathematical friends sit in their studies, and out of their minds they dream up the beautiful patterns of pure mathematics. If maths isn't your subject, just think of it as being a pattern, organizing, pattern discovering type of discipline. What we are saying is that some of the most beautiful patterns that the mathematicians can think about are found actually to occur in the world around us. What ties the two together? Well, of course, a deep question like that, why is science possible, why is mathematics so unreasonably effective, a deep question like that won't have a knockdown answer. But to me, a coherent and satisfying, and to me the best answer, is that the reason within and the reason without fit together, because in fact they have a common origin in the mind of God, whose will is the ground both of my mental experience and the existence of the physical world, which I am a part. They're tied together in that sense. You could say that as fundamental physicists explore the wonderful structure of the world, they are exploring a world that seems shot through with signs of mind in its rational order and rational transparency and rational beauty. And it is at least worthwhile considering the possibility that it is indeed the capital M mind of God that lies behind this order. And of course, I believe that's so. That makes, in other words, a religious belief makes intelligible the fact of the intelligibility of the universe. science itself would explain it. It is very happy to exploit and explore the possibilities that produces, but it doesn't of itself explain it. The second thing about the world, of course, is that its history has been amazingly fertile. You all know that the universe started 13.7 billion years ago. Cosmologists are really getting accurate these days. 13.7 billion years ago, as an almost uniform expanding ball of energy, of just about the simplest physical system you could really think about. One of the reasons why cosmologists talk with a certain justified confidence about the very early universe is that it is easy to think about. That world that started so simple has of course become rich and complex, with you and me actually the most complicated consequences of its unfolding history, at least of which we are aware. The human brain, we've heard a bit about it this morning, very interestingly, actually you seem to be reducing the number of neurons. I used to say 10 to the 11, which is the same number of stars in the Milky Way, but it's gone down by a factor of 10. Not as many neurons, not as many genes. Biology is simpler than we thought. It's still a bit complicated, I think I have to say. The human brain, anyway, particularly with its immense connectivity, is far and away the most complicated physical structure we've ever encountered in our exploration of the world. The mere fact that simplicity has turned into rich complexity in itself might suggest that something has been happening in cosmic history. But the way in which it's happened, of course, has been through evolutionary process, and at every stage of the story. Not just the familiar story of the evolution of terrestrial life, but also, of course, the cosmic story of the evolution, the coming to be of stars and galaxies and so on. That was also an evolutionary process, meaning by that a process in which you have a fruitful interaction between chance and necessity. Chance standing not for capriciousness, but for the contingency of actual happenings, and necessity standing for the lawful regularity of the world. The very early universe, so it was almost uniform, but not quite. There were little fluctuations. There was a little bit more matter here than there. That's contingency. If there's a little bit more matter here, it has a stronger gravitational pull. It draws in further matter. You get a snowballing effect. And after about 1 billion years, the universe becomes grainy and lumpy with stars and galaxies, an absolutely indispensable part in the fruitful unfolding of cosmic history. It's a very deep and interesting scientific insight that regimes in which new things emerge are always regimes which are at the edge of chaos. Those are the places where true novelty can come into being. You need a mixture of order and disorder, of chance and necessity. If things are too orderly, then they're too rigid for anything really new to happen. You can get rearrangements, but you don't get entirely novel structures coming into being. If things are too haphazard, then of course new things might happen, but they will disappear. They will simply fade away as quickly as they, like smoke really, as soon as they're formed. So to have persisting fertility, you need an interplay between chance and necessity. You need to be at the edge of chaos. That's a very powerful and general insight, it seems to me. And it relates to a question that is, of course, very puzzling in a way for theology, namely the existence of the shadow side of creation. The disease and disaster that are such a striking aspect of the world that is also beautiful and fruitful in its history. And we have to take both of those into account. And what right at the start, in 1859, when Darwin published his great book on the origin of species, the picture that all the scientists shouted yes and all the religious people shouted no is just ignorant and wrong. There were religious people who welcomed Darwin's insights from the start. Charles Kingsley would have been one of them. And he coined the phrase that I think is the way to think theologically about an evolving world. He said God could no doubt snap the divine fingers and brought it into being a ready-made world. But God had done something cleverer than that, in bringing into being a creation in which creatures could make themselves. That's what an evolving world is, through the shuffling explorations of chance at the edge of chaos. Creatures are allowed to bring to birth, in their own way, the immense potentiality and fruitfulness with which the Creator has endowed the universe. That's a wonderful, I think, a better world than a ready-made world would have been. It's a fitting creation of the God of love, who is not the cosmic tyrant, the puppet master pulling every string. Creatures are allowed to be themselves and to make themselves. It's a world of of great wonder and fruitfulness, but it is inescapably has a shadow side to it. The explorations of chance will bring into being new forms of life. They will also result in ragged edges and blind alleys. Biological mutation, and biological evolution rather, has been driven, of course, by genetic mutation, and that's produced new forms of life. But inevitably, if germ cells are to mutate and produce new forms of life, it will be possible also for somatic cells to mutate and become malignant. You can't have one without the other. In a non-magic world, and the world is not magic because God is not a capricious magician. So there is a shadow side to creation. I don't suggest for a minute that removes all the anguish or indeed anger that we feel about the strangeness and bitterness of this beautiful and fruitful world. But it does at least show, I think, that it's not something that's gratuitous. You see, we all tend to think that if we'd been in charge of creation, we would have done it better. We would have kept all the nice things, the sunsets, the flowers and all that, and thrown away all the nasty things, the disease and disaster. But the more science understands the processes of the world, the more we see that these things inextricably intertwine. You can't pull them apart, keep this and throw away that. So the fact that there is cancer in the world is a terrible fact about the world, undoubtedly. But it's not something that a God who is a little bit more competent or a little bit less callous could easily have dealt with. It's the inescapable cost of a world in which creatures make themselves. You could argue about whether that's a worthwhile cost to pay, but that, I think, mildly helps theology as it struggles with the problem of human suffering. The other thing to say about evolutionary process, of course, is that it is both chance and necessity. If you read, as I'm sure somebody would have done, Jacques Monod's famous book, Chance and Necessity, it's all about the chance side of things, as he would say, the fortuitous side of what's going on. But we've also come to realize, as we've understood the history of the universe, that the necessity side has to be very particular as well. Evolutionary process won't produce the astonishing effects it has in our universe, in any old universe. The given physical fabric of the world has to take a very specific, very finely tuned form if the evolution of carbon-based life is to be a possibility. That, of course, is the collection, vast now collection of scientific insights that's gathered together under the rubric of the anthropic principle. A world capable of producing anthropoi, I mean not literally five-fingered Homo sapiens, obviously, so there are contingent things about us, but beings of our complexity is a very special world indeed. I'm sure you all know about that. Just let me remind you of one thing. Carbon-based life. Where does carbon come from? Well, of course, there's no carbon in the early universe. The early universe is too simple to make things like carbon. It only makes the two simplest chemical elements, hydrogen and helium. And they have a pretty boring chemistry. You can't do very much with hydrogen and helium. That's all you've got. You've got to get going, and to get going, the first heavier element you want is carbon. And of course, if you could make 3 helium nuclei stick together, that would turn helium-4 into carbon-12. But it's very hard to do that. With very small things, you can't stick 3 together at one time. You have to do it sequentially. You have to stick 2 together, that would make beryllium-8, and then you have to stick the hope that at least in some cases a third helium will stick on and turn it into carbon-12. But the trouble is, the beryllium-8 is very, very unstable. It doesn't stay around long enough in a normal way to have any chance of acquiring that extra helium nucleus. And Fred Hoyle, a colleague of mine here in Cambridge, who played a very, very major role in understanding how the elements are made inside the stars, was absolutely baffled and frustrated by not seeing how to make carbon-based life. How can I make carbon? Though, of course, he knew it must be there because he's carbon-based life like you and me. And then he saw that it would just be possible if there was a large enhancement effect, a resonance in carbon at exactly the right energy. It had to be the right energy to work in the processes going on inside stars. It had to be there. And he said, that's it, eureka, I know how carbon's made. So he went to the nuclear data tables just to check out that there was this resonance at this energy in carbon, and it wasn't there in the tables. But Fred was so convinced that it must be there that he rang up some friends of his in California who were very clever nuclear experimentalists, the Laurisons, father and son, and he said, look, you chaps have missed something. there's a resonance in carbon that you haven't seen, and I know where it is. I know exactly where it is. I'll tell you where you look to find it. They weren't very keen to do that. I don't know why. It was perhaps a tricky experiment. I don't know. But of course they did in the end, and there it was. I mean, that's a wonderful, wonderful scientific story. I'm afraid Freud got a Nobel Prize for it, but that's another thing. But Freud, who had a lifelong conviction of atheism, also realized that if the laws of nuclear physics had been a tiny bit different, either there would be no resonance at all, or it would be somewhere else, and if it was somewhere else, that wasn't any good either. So, in other words, the possibility of carbon-based life depended upon the laws of nuclear physics essentially being what they are in this world. And he's said to have commented in a Yorkshire accent that's beyond my power to imitate, that the universe is a put-up job. This couldn't be just a happy accident. There must be some reason for this. And because Fred didn't like the word God, he said there must be some capital I intelligence in fixing the laws of nature. Well, there again, there's the problem the necessity has to take a very specific form. And that again seems to be a non-trivial fact about the universe, something we shouldn't just shrug our shoulders and say, well, just the way it happens to be, bit of good luck for us. Romney's written a book that discusses these issues in great detail. But certainly, if you take the view of the universe as being a divine creation, you have immediately a coherent explanation of why the laws of nature are fine-tuned for life, because they are the expressions of the will of a creator who wishes the universe, his creation, to have a fruitful history. So intelligible and fertile, these things, these are just facts that science has to treat as brute facts, as given facts, on which it then builds its story and its explanation, but which do seem to point beyond science itself and call for some meta-scientific explanation. And theistic belief certainly provides a coherent, and in my view, fitting explanation of that. Now the third thing about the universe that we've discovered, and particularly the discovery of 20th century physics, is that the universe is intrinsically relational in its character. In the 18th century, following Newton, and the 19th century, the picture of the world essentially was of atoms rattling around in the given container of space in the course of the unfolding of a universal time. But that, as you all know, that picture was totally changed in the 20th century by Einstein's great discoveries, first of special relativity and then of general relativity, the modern theory of gravity. And in that theory, space, time and matter are all intricately related to each other. They are a package deal. Matter curves the shape of space-time, and the curvature of space-time influences the paths of matter through it. That's the modern theory of gravity, the source of gravity. Einstein, in general relativity theory, turned physics into geometry. An interesting move. So space-time and matter belong together. Of course, an insight that that clever man Augustine had thought of 13 centuries before Einstein, when he realized that when God created the world, God brought into being both space and time and matter. There was no before creation, because there was no time until God had created it. So that was one aspect of rationality present in the physical world. But an even more striking discovery, again associated with Einstein, was quantum entanglement. You know, Einstein had been the sort of grandfather of quantum theory for his explanation of the photoelectric effect. But he hated his grandchild. He didn't like the way quantum theory developed. He didn't like its cloudiness, its fitfulness. He didn't like them because he mistakenly thought the reality is the same as objectivity. And if the physical world wasn't unproblematically objective, it wouldn't be real. That's a mistake. And I'll come on to that in a minute. But, so we always trying to find something wrong with quantum theory. And he showed, with a couple of young colleagues called Podolsky and Rosen, showed in the 1930s that quantum theory implied a quite entirely counterintuitive togetherness and separation. That once two quantum entities had interacted with each other, then they would remain intimately connected with each other, entangled with each other, however far they might separate. One of them might stay here in the laboratory, the other might go beyond the moon, as we conventionally say. But if you did something with one in the laboratory here, it would have an instantaneous effect on the one behind the moon. Because they had once been interacted, they had essentially become one system, even though they might spatially separate. Einstein thought that idea was so spooky that it showed there must be something wrong. But very much later on, in the 1980s, following some very clever theoretical analysis by John Bell, the experimentalists show that this non-locality, this quantum entanglement, is indeed a property of nature. So you have this ironic discovery that the subatomic world cannot properly be treated atomistically. The world is much more interconnected than we'd ever realized before. And I think we're still struggling in many ways, both in terms of physics and in terms of metaphysics, to come to terms of what exactly this means about the structure of the world. It used to be thought that separability was unproblematic, and then you had to argue about how things might affect each other. Now it's the other way around, really. The fact that there is an effective separability in our everyday experience of the physical world is the thing that we still have to do a bit of struggling to understand. It's very important to realize this connection between these two quantum entities is truly ontological. It's not an epistemological thing. I mean, there's nothing paradoxical or surprising whatsoever about gaining knowledge at a distance. I mean, if there is a white ball in an urn and a black ball in an urn, you and I both put our hands in, each of us takes one ball in a closed fist. I stay here, you go down the road. I open when you're 2 miles away, I open my fist, I see I've got a white ball. I immediately know you've got a black ball. That's nothing surprising about that. You always had the black ball, and what's happened is I know that's the case. But this relationship between these quantum entities is genuine. It's not epistemological. It's genuinely causal. What I do to the one here has a causal effect on the one behind the mirror. It's as if I found a green ball, you'd have to have a yellow one. If I had a blue ball, you'd have to have a red one. It's very surprising, but it's there. So the world is deeply relational, and there are other ways which I can elaborate as well, but that's enough. The 20th century physics was discovered there. And though that doesn't, of course, prove that the world is the creation of the Trinitarian God, it's at least deeply consistent with that belief. And indeed, again, in this theology of nature realm, Trinitarian understanding that God, the essence of the divine being itself is relationality. It does cast light on the character of the creation that triune God has brought into being and maintains in being. Well, I suppose one of the most influential books on Trinitarian theology, second half of the 20th century, was John Zizioulis' book, Being as Communion. Well, scientists have discovered that reality is relational, and there is a clear consonance between those two discoveries. Fourth thing about the world in which we live that science has discovered is that its character, in fact, is elusive. It is veiled. It's a veiled form of reality. And here, of course, we come back to quantum theory. The quantum world is a strange world. It is not a naively objective world in the way that Einstein wanted it to be. It is a world in which if you know where something is, you don't know what it's doing. If you know what it's doing, you don't know where it is. That's Heisenberg's uncertainty principle. It's a world of cloudiness and of truthfulness. We cannot predict with certainty, or usually we cannot predict with certainty, the outcome of an experiment. We can say that maybe you'll find it here, maybe you'll find it there. And we can predict the probabilities extremely accurately. I mean, quantum theory is fantastically accurate, far and away the most accurate scientific theory has ever been. The behavior of electrons and photons can be so precisely predicted that the uncertainty between experiment and prediction is equivalent to the width of a human hair in relation to the distance between Los Angeles and New York. That's a very, very accurate theory. I think I might, on a slightly physicalist, triumphalist note, draw your attention to. So the quantum world is nevertheless elusive and veiled from our side. It's quite different from the world of every day. And there are two sort of general conclusions I think one can draw from that. One is not to make Einstein's mistake. Einstein wanted there to be a universal epistemology, that you knew the whole of reality in the same way. It's a very attractive aim, but it is quite clear that it is an unattainable aim. The essence of rationality is to seek to understand things in the way that is appropriate to their nature, to conform our thinking to to the nature of that which we're trying to think about. And the difference between Newtonian everyday classical physics, with its clarity and reliability, and the veiled quantum world, with its cloudiness and fitfulness, tells us that there is no, even in physics, there is no universal epistemology. We shall not truly know the quantum world unless we are willing to acknowledge that we know it according to its Heisenbergian nature. We demand of quantum physics that it will have the transparency and clarity of Newtonian physics. We shall just fail to understand quantum physics altogether. So there is no universal epistemology. We have to know things according to their natures. That's true in the physical world, and of course it's true when we move beyond the physical world. We know each other as persons in a different way from the way in which we know tables and chairs. Tables and chairs, I can sort of submit them to whatever I want to do to them. I can chop them up if I want to. People I have to know in a different way. I have to know people only not through testing so much, but through trusting. That's the form of our encounter. And of course, we know the transpersonal reality of God in a different way again. We can only truly approach God if we approach God with awe and worship and reverence and obedience, so that there is no universal epistemology, no universal form that rationality has to take. It seems to me that the instinct of a scientist is not to ask about any proposition, actually, not to ask the question, is it reasonable? As if we knew the shape the rationality had to take beforehand. Nobody in 1899 would have thought quantum theory was reasonable. Nobody would have thought that something could be both here and there. I mean, it's an absurd thing. Nobody would have thought that something could sometimes be a wave, sometimes behave like a particle. I mean, waves are spread out and flappy, particles are little bullets. How can you possibly combine the two? It's obvious nonsense. But of course, that's the way, actually, the subatomic world turns out to be. So our instinct, it seems to me, as scientists, is not to ask, is it reasonable? Because the shape of rationality can be very surprising. But our question, an actual question and a proper question, I think, is what makes you think that might be the case? You see, on the one hand, that's a more open question. It doesn't try and specify beforehand the shape that a reasonable answer has to take. But in another sense, it's a demanding question, because it says, whatever understanding you're going to offer to me, I want to have motivating evidence for it. That's what I sometimes call bottom-up thinking. The approach where you try and approach reality in terms of taking seriously experience and then trying to move from the basement of experience to the ground floor of understanding, rather than top-down thinking where you start in the 10th floor of general principles and try and descend to particulars. So our question, I think, is what makes you think that might be the case. And that's a question that I think we can ask not only about our scientific understanding, but also about our religious beliefs. I'm very happy to try and approach religious belief, Christian belief, in that sort of bottom-up thinking way. In fact, I wrote a book which in North America is called The Faith of a Physicist. In this side of the land it's called Science and Christian Belief, which exactly tries to address the central tenets of Christian belief in exactly that sort of spirit. So there's no universal epistemology. There's another lesson I think we can draw from quantum theory, or a general lesson. That's that. I mean, quantum world is strange. So is it really real? I mean, Einstein was convinced about that. I suppose all most scientists are, because after all, why should we spend our lives trying to understand the physical world if we didn't think we were actually understanding what it's like? But how can we defend the reality of an elusive thing like an electron, sometimes here, sometimes there, sometimes both at once? I think the ground for our belief in the reality of electrons essentially is intelligibility. It is because belief in electrons makes intelligible great swathes of more directly accessible experience. It explains to us chemistry, it explains to us superconductivity, it explains to us how people will make electron microscopes and so on. Intelligibility is, I think, the underwriting of our belief in the reality of some entity. That's a thought which is very much concordant, really, with the sort of Thomistic strain of thinking in Christian theology, which tries to hold together faith and reason in mutually enhancing and supporting ways. The great Thomistic theologian of the 20th century, Bernard Lonergan, Jesuit, Canadian Jesuit. He wrote a big and difficult book called Insight. And the thesis of that book essentially is that intelligibility is the key to reality. That's true, I think, again, throughout the whole spectrum of human experience. As a physicist, I speak about unseen realities. Some intrinsically unseeable realities, quarks and gluons, which I passionately believe in, constituents of nuclear matter, are, we believe, confined. They will never be expelled from the matter that makes them up. We shall never see an isolated quark on its own in the laboratory, so we believe. Nevertheless, we believe in their reality because, again, it makes sense of great swathes of, in this case, physical experience. So science believes in unseen realities if they grant deep levels of intelligibility. And of course, I would say that our belief in the unseen reality of God can equally be supported by the intelligibility that belief grants to a whole swathe of human experience, both spiritual and also of the kind of experience that we're discussing in this lecture this morning. So the elusive world is veiled from our sight, but it is real. And it means there's a cousinly connection, I think, between quantum physics and theology in that respect. In fact, here's the commercial. I've got a book coming out in March, whose title, curious enough, is Quantum Physics and Theology. And it seeks, by looking at a dozen or 14 paired insights, discoveries in physics and in theology, to establish this cousinly relationship. Next thing that science has discovered about the physical world, and again this is 20th century science, is that it contains intrinsic unpredictabilities. You all know about that. You all know that the first area in which that came to light was indeed again in quantum physics, the intrinsic unpredictability of, say, the decay of a radioactive nucleus, something like that. And then you also all know that subatomic unpredictability was complemented by the discovery, or rediscovery in a sense, in the 1960s of intrinsic unpredictability at the macroscopic everyday level through chaotic dynamics. That there are these systems, in principle describable by Newtonian dynamics, in other words, apparently the sort of clockwork type of universe, but the universe is not clockwork, it's something more subtle than that. And it is full of systems that are so intrinsically sensitive to the minutest details of their circumstance that their future behavior cannot be predicted. There are many clouds in the world, as well as clocks. You all know about that. You all know about the butterfly effect, that the Earth's weather system can be in so sensitive a state that it's a serious scientific joke. The best jokes are always serious jokes. A serious scientific joke to say that a butterfly stirring the air with its wings in the African jungle today could produce consequences that grow and grow and grow and grow until they produce a storm over East Anglia in about 3 weeks' time. So the world is full of intrinsic unpredictabilities. And we really do mean intrinsic. These aren't things that more exact measurement or more clever calculation could remove. They are, in principle, barriers to human knowledge. And then, of course, that's a very interesting discovery. The question then is, what do we make of that? And, of course, predictability or unpredictability is an epistemological property. It tells us what we can know or what we cannot know about the future behavior of a system. And it is a fundamental problem in philosophy, and perhaps the fundamental problem in the philosophy of science, what relationship we should postulate between epistemology and ontology, what we know and what is actually the case. There is certainly no inevitable entailment from one or the other. It requires a philosophical or metaphysical decision about what connection we should make. You all know that Immanuel Kant, for example, very much disconnected the two. I mean, Kant believed that we were aware of phenomena, the appearance of things, but we have no knowledge of noumena, what things are in themselves. That's a sort of counsel of ontological despair, really. The other extreme is realism, and the realistic position says that what we know is a reliable guide to what is the case. My wife years ago gave me a sweatshirt with the series motto, epistemology models ontology, written on it. Beautiful words that you'd often heard me speak. And what that's saying is that what we know really is a reliable guide to what is the case. That's the realistic view of the world. It's what scientists, I think, both consciously and unconsciously believe, almost all of them. Again, because if we didn't feel we were learning what the physical world is actually like, or the biological world, what would be the point of it all? So, but you have to make up your mind whether you're going to be a Kantian or whether you're going to be a realist or somewhere in between. And it is a philosophical choice. Well, if I take the realist choice, which is what I do, then unpredictabilities will be naturally interpreted not just as unfortunate deficits in human knowledge, but as ontological opportunities, an openness in the process of the world. The possibility of the existence and operation of causal principles beyond those which have been described in traditionally reductionist terms by science, namely the exchange of energy between constituents. It's very important to realize that questions of causality, though they are influenced by scientific discovery, are not settled by scientific discovery. Questions of causality are metaphysical questions which receive metaphysical answers which have to be defended for metaphysical reasons. Science constrains metaphysics in the same way that the foundations of a house constrain the edifice you can erect upon it, but science does not determine what that metaphysical edifice should be. And you can see that very clearly by going back again to quantum theory. We conventionally think of quantum theory as being indeterministic. It's undoubtedly probabilistic, there's no question of that we can't predict what's going to happen in most circumstances. But that could be for two reasons. It could be because there is an intrinsic, in principle, indeterminism present in the system, or it could be because we are just ignorant of all the causal factors that actually determine what is going to happen. And it turns out you can interpret quantum theory either way. The conventional interpretation of quantum theory, which is one actually I myself subscribe to, which goes back to Niels Bohr and so on, is that there is an intrinsic indeterminism in quantum physics. Heisenberg's uncertainty principle is a principle of indeterminism. But there is an alternative interpretation of quantum theory due to a very clever chap called David Bohm, which takes the view that the probabilistic character of quantum theory arises just from ignorance of fine detail of hidden variables, the extra variables that determine exactly what's going to happen. For Bohm, Heisenberg's uncertainty principle is just a principle of necessary ignorance, no more than that. It's mere epistemology. And the interesting thing is that Bohr or Bohm have exactly the same experimental consequences. So no scientific experimental judgment can choose between the two. That illustrates the point that causality is not settled by science alone. So why do most of us vote for Bohr rather than Bohm? Well, I think one of the reasons, there are several reasons actually. One of them will do. Bohm's theory is very clever, but most of us think it's too clever by far. It sort of has an air of contrivance about it. Bohm does his trick by having both particles and waves. His particles are as unproblematically objective as Isaac Newton could ever wish them to be. But there is this hidden wave which permeates the whole universe and which instantaneously records the state of the whole universe. And it influences the movements of the particles. So it is a sort of non-local effect. Every bit of the wave, so to speak, carries information about the whole cosmic context in which things are taking place. That's a very clever idea, and that's how he's able to do it. But of course, if he's got a wave, he's got to have a wave equation. And what equations has he got for his wave? Well, you will perhaps not be altogether surprised to learn. It turns out the wave equation is the Schrödinger equation. And where did Bohm get that from? He got it from Schrödinger. And if he hadn't taken it from Schrödinger, he wouldn't have got the right answers. So there is an air of contrivance about it. Now, you see, that's not a scientific judgment, strictly speaking. It's a metaphysical judgment. This theory is, as I say, too clever by heart. Now, if we take the realistic interpretation, our unpredictabilities, their widespread character in the world implies that there must be a certain openness of the world to its future. not everything is settled by the reductionist bits and pieces, nitty-gritty account of science itself. It doesn't follow from that the future is some sort of random lottery. It simply means that there are conceivably other causal principles at work in the world, in addition to the reductionist energy exchange between constituent account that science offers. And what could those principles be like? Well, a pretty obvious possibility would be human agency, it seems to me, in fact, where we were this morning. Certainly, an honest science has not demonstrated the causal closure of the world on its own terms. And therefore, it is not in a position to forbid me to believe that when I raise my arm, which is the example I usually use when giving this talk, though there's of course the bits and pieces account that we heard of, it is I who raise my arm. There's this sort of holistic causality of agents at work in the world that I think we experience directly. Again, I share it with Bill, the fact that if you don't accept that, you have lots of problems about rationality, quite apart from freedom of the will. So I think that's one, and also I think, of course, divine providential agency. I mean, if God, we are able to act as agents of the world, it's going to be very surprising, really, if the creator of the world had not left himself some room for causal manoeuvre in the unfolding history of the world. So I think we can take those things in that sort of way. Let me make two comments on that. One is this. If I'm right in thinking that intrinsic unpredictabilities are the source of this power of agency in the world, it means that the acts of agents are always to some extent going to be hidden in the cloudiness of unpredictable process. It will not be possible to itemize the world and tear apart the things that happen in it. To say natural law simply did this, human agency did that, divine providence did the third thing. They'll all be entangled with each other in the cloudiness of unpredictable process. So though I think providential action may be discernible by faith, it will not be demonstrable by experiment. That's one thing I want to say. The other thing I want to say is that while we have learned about these unpredictabilities at the quantum level and at the chaos level, again, I don't think for a minute that our agency or God's agency is actuated by scrabbling around either at the subatomic level or at the cloudy system. It's much more complex than that. We just happen to know about these two levels. They're the clues we have. But the causal structure of the world is much more complex and subtle than that. And I think it's an integrated causality. It operates at all levels at the time. So that I don't think we should think about it that way. And you can see that again by the fact that you might think, okay, we've got quantum theory, we've got chaos theory. These chaotic systems are so sensitive that very soon their future behavior is going to depend upon a degree of detail that actually falls within the uncertainty principle. So why not put quantum theory and chaos theory together, and then you've got an expanded theory open to the future. It seems an obvious thing to do, but it doesn't work. The reason it doesn't work is that we cannot reconcile chaos theory and quantum theory in a consistent way. We can't just put the two together, they don't fit. The reason for that is quite simple. Quantum theory has an intrinsic scale to it, which is set by Planck's constant. Chaos theory is fractal in its character, we all know that, and fractals have no scale. They are the same on every scale. And you can't put a scale-free theory and a scale theory together in a consistent way. So nobody knows. Quantum chaology is one of the big problems in physics. Nobody knows how to put these two together. And that, again, is an illustration of the necessary subtlety that awaits exploration as we try and learn a little bit more about the shape of the causal nexus of the world. But at least, as I say, science has not demonstrated that that causal nexus is incomplete. Is complete on science's own terms. Another little advertising remark I create. My latest book is called Exploring Reality, and there's a quite long chapter in that about the causal nexus of the world, which tries to set these things out in a more systematic way. The sixth and final thing I think we learned about the world is that it is a world characterized by something we might call information generating. The spontaneous generation of quite unexpected structures. Scientists are just beginning, in a very small way, to be able to study the behavior of complex systems in their totalities. I mean, the technique of science in dealing with complex systems has either been the reductionist technique of divide and rule, methodologically a very fine technique, and we learn lots of things that way, to split them into their component parts, which are easier to understand. If we can't do that, then the other technique that science has used for the last 150 years, I suppose, is the thermodynamic approach of averaging over the coarse-grained behavior of very large systems of 10 to 23 molecules or whatever inside of them. Now we're just beginning in the smallest way conceivable to be able to explore systems in their totalities. There's somewhere between those two extreme limits. This is so-called complexity theory. A lot of that work is being done in terms of computerized models, and some of it has been done in terms of physical systems, so-called dissipative systems, which are held far from thermodynamic equilibrium by the exchange of energy and entropy with their environment. I'll stick with the computerized models for a minute. Stuart Kaufman, whose writing will be familiar to some of you, is the person who has done a lot of exploration in this sort of area. He wrote a book called At Home in the Universe, which is a fairly accessible account of his ideas. And what people have found with these systems is that they, of course, these systems that people are able to study on computers are nothing like as complicated as a single living cell. I mean, other than anything else. I mean, they're toys of thought, really, but they're interesting. And here's one of the systems that he's explored. It's a logical system, because it's a computerized system. Logically, it's a Boolean net of connectivity too, but if we don't want to speak that language, we can think of it in terms of a sort of hardware equivalent. Suppose you have a great array of electric light bulbs. Now, each of these bulbs can be in one of two states. Either it's on or it's off. And each bulb in the array is correlated with two other bulbs somewhere else in the array. And the array is going to develop in steps, according to a perfectly clearly set out set of rules that correspond to this Boolean connectivity. And what this bulb is going to do at the next step is determined by the state of these two correlate bulbs at the present step. We don't need to go into the details of the correlation, they're pretty straightforward and simple. So you set this system up in some sort of random pattern of illumination, some bulbs on, some bulbs off. You then let the system evolve according to the rules. Now, I don't know what you guess. I don't guess nothing very interesting can happen. It would just sort of flicker away in some haphazard way for as long as you let it happen. But in fact, that doesn't turn out to be the case at all. It turns out that very, very soon, the system settles down spontaneously into an extraordinarily ordered form of behavior. If you have 10,000 light bulbs in the array, the number of possible states of illumination is, of course, 2 to the 10,000, which is, roughly speaking, 10 to the 3,000, which is a pretty big number, I think, in anybody's book. But it's found, just experimentally, that very soon the system will settle down to cycling through just about 100 different patterns of illumination. I mean, that's the most astonishing generation of order that you can imagine. Every time I tell this story, and it's one of my favorite stories, every time I tell this story, I'm just sort of bowled over by that. So what's going on? Well, actually, we don't know. I mean, there must be some theory that lies behind this spontaneous generation of order in complex systems. But that theory has not yet been attained. Complexity theory, so-called, is really complexity in natural history. It's at the stage of saying, gee, it's happened again, and looking at for instances. But there must be some deep theory behind this. No doubt it will be discovered one day. And when it is discovered, I think that the character of that theory is fairly clear, even if we don't know what its details are going to be. First of all, it's going to be a holistic theory. These are properties of systems in their totalities, properties you couldn't possibly foresee in terms of the individual elements making them up. So it will be holistic theory rather than a constituent theory. And it will be concerned with the generation of dynamical patterns of behavior. And so its fundamental concept, I think, or fundamental category, is going to be something like what you might call information, the specification of dynamical pattern, rather than, say, energy, which is the fundamental concept for constituent theories. And I venture to guess that at the end of the 21st century, it won't be here to see it, but I venture to guess that something like information would have taken its place alongside energy as a fundamental category and scientific understanding of the world. We're far from that at the moment, it's going to come. Now that's a hopeful idea. I mean, it's only a small step, but it's a small step in a hopeful direction. Because when we think about our own intentional behaviour, something like active information seems to be being expressed through that. I execute my intention of raising my arm. If we think about God's interaction with the unfolding history of the world, again, you can think of that in terms of some sort of input of information shaping and forming the history of the world. I mean, we're very far, I mean, it's a big, big step between Kaufman's stuff and anything that an anthropologist or a theologian would want to say. But at least I say there's a helpful direction in which the way wants had. Thomas Nagel's I'm a great admirer of him too, and he has a wonderful phrase in his book, The View from Nowhere. He's talking about attempts to understand human agency and intentionality. He says, the best we can manage is pre-Socratic flailings around. It's a wonderful, wonderful, wonderful phrase. You know, Anaxagoras and Anaximander, all these pre-Socratic philosophers, they have this wonderful idea that maybe the rich complexity of the world is all formed out of a single basic stuff. They had different ideas about what that might be. Somebody said air, somebody said water, and so on. But it was a very clever idea. It was, in fact, the beginning of elementary particle physics. But it was, of course, 2,500 years too soon. Actually, you get on to quarks and gluons. But it was a clever idea. So they were waving their hands in the right direction, but they were certainly waving their hands. And I think we're about in that same position in relation to all these questions that have been discussed this morning, so hopefully interesting. And we have to be wary about not getting too carried away by the discoveries of complexity theory. The final thing I want to talk about is this question of emergence. I think emergence is a very, very important concept. A lot of things are going, a lot of exploration going on at the moment. A very useful little book that I see on the bookstall down there is Philip Clayton's book, Mind and Emotions, which I think is worth reading. But we have to be careful about it. And the key question is the question that Bill has put to us already. Of course, there is the emergence of structure. Of course, there is epistemological emergence of concepts. I mean, all these thermodynamic concepts emerge in that sort of sense. The wetness of water is not a concept that relates to a single H2O molecule. You have to have a lot of them. When you have a lot of them, the energy distribution is shifted by their mutual interactions, and you get a surface effect that scientists call surface tension, and we experience as wetness. That's an unproblematic sort of emergence. I mean, it's hard to figure out things like how surface tension exactly works, but I think there's no doubt it's just a reassortment of energy due to interatomic forces. That's an unproblematic emergence. The key question is there also ontological emergence? Is there something genuinely new that comes into being? And I think that's connected with the question of, is there causal emergence? Is there really a new form of causality acting in the world? Now, top-down causation is a very attractive, very beguiling notion, and I think that, I aspire to use it like everybody else. But it's not an unproblematic. We tend to think it's unproblematic because, again, we tend to feel we have direct experience of it. But when you think about it, you have to be careful not to be too quick in evoking top-down causation. And the reason for that is, it seems to me that causality is a zero-sum game. And if the causal effects among constituents soak up the whole of causal room for manoeuvre, then there is no top-down causality of a true kind. And that's a possibility, which Kaufman's model, which I've just described, illustrates. Kaufman's model is implementable upon a computer. It follows these Boolean laws. It is strictly deterministic, and the determinism comes from below. There is no top-down organizing principle that causally causes this particular cycle to take place. So it's an example of astonishing holistic behavior, and presumably appropriate concepts that go with that behavior, but which is totally determined from below. There is no ontological emergence, it seems to be, in the Kaufman text. Now, because of the possibility of interpreting physical unpredictabilities realistically, that isn't, I think, clearly true for living beings, for ourselves, and so on. I mean, there is a possibility that there is true emergence there. But that's something that we have to try and work for, and we have to be careful not to be too quick, I think, in appealing to it. Well, there we are. We had a sort of tour d'horizon of science things about the about the universe. It seems to me that we live in a world that is rich, it's amazingly surprising, amazingly subtle. I think amazingly supple in its structure. It is also intrinsically interrelational in its character. I think it is a world that is, from an overall perspective, is fittingly understood, and most fittingly understood, as being the creation of the Trinitarian God, the one for whom being is communion, and whose creation is one in which reality is relational. It makes sense of it in that sort of way. Not in the sense that my atheist friends who don't share that view are stupid, because obviously they're not. But I do think that theism explains more than atheism is able to do. That's what I think, and now you can tell me what you think.
Thank you. That encapsulated an awful lot, I'm sure. For many of us, it's the first time we've heard some of that. We're reeling a bit. But no, excellent talk. Thank you very much, John. So, questions, please.
Or comments, of course.
Yeah.
Can I go right back again, being totally layman in this business of reality and intelligibility,
Right.
which is obviously fundamental to what you're saying, really. That we defend the reality of these models at the subatomic level because they explain other things.
Yeah.
Is it not possible that sometime in the future there'll be a different model which actually does fit our rationality better?
Well, that's the risk. Yes, I mean, Bill Newton Smith, who writes on the positive science, talks about the pessimistic induction, which is that any scientific concept will prove after 200 years to have been replaced by an alternative concept. So you can sort of argue, obviously, history not this way. Yes, there is a risk involved in that. I think myself that, first of all, I think it's, philosophers of science tend to concentrate too much on the early period of science, where things were much more fluid than they are today. I think in well-winnowed scientific domains, there is going to be a stability of understanding. It will be extended in various ways and modified in various ways. But there is a risk involved in that. And we have to be aware of that risk. We have to, you know, the familiar statement that he who marries the spirit of the age will be a widower before he knows where he is. We have to bear that in mind. But equally, of course, we have to do the best with what we've got. I think the things that I've talked about, I think I'm trying to indicate whether there's a aspirational and not yet worked out aspect to them. But I think the most, broadly speaking, what I've said will survive. There may be other, I hope there will be, other insights that will extend and enrich that. But yes, I mean, we have to make some bets. I mean, it's a very important recognition that human knowledge is intrinsically, I think, precarious. The philosopher of science I like the best is Michael Polanyi, who was, of course, a distinguished physical chemist before he became a philosopher. And he wrote Personal Knowledge to indicate that science is not certain in some sort of factual, provable sense. He said, I'm writing this book to explain how I may commit myself to what I believe to be true, knowing that it might be false. That's Polanyi on science, and I think that's the human situation with respect to all forms of knowledge, including, of course, religious knowledge. I mean, that's the commitment to faith, that we commit ourselves to faith in the God, Father, and our Lord Jesus Christ. Not unmotivatedly, but not certain beyond a peradventure.
Thank you. Yes.
I'm fascinated by your Boolean dialogues,
Yes.
and rather encouraged that you don't seem to really understand what's going on. I have a kind of imaginative question, which might just be ridiculous. I was trying to see them at 3 dimensions, or more dimensions, and wondering whether there's any speculation about what might go on if you increase the complexity of this model.
Well, of course, because it's a logical model, it doesn't in any, it's in logical space, but not in any form of physical space. So changing the dimensions would be to change the connectivity. I mean, there were 2 correlates in this sort of thing. You could have connectivity 3 and so on. And for reasons that I think Kaufman explains in his book, which I can't remember, he concludes on the whole that connectivity 2 is the best. You see the most interesting things happen, at least at the level at which he's able to implement it on a computer. Certainly changing the connectivity will change the behavior of the system. But he wrote this book called At Home in the Universe, and chapter 4 is all about these models in that book, and it's a readable read. It's a Penguin book, so it's worth, if you're really interested, I mean, I'd say go and read it. He's also written lots of other things that are much more technically demanding. At least I find them so. Well,
Yeah.
Well, when you were talking about the unseen,
right.
the intelligibility of unseen
Right.
realities,
Right.
and that made me think of the spiritual reality, which working in Africa is very prevalent and always around us, and very much a part of the system of reality and the worldview of everyone in Africa.
Yeah.
Do you foresee any time in which science may, just like quarks and gluons give us an insight into an unseen reality of particle physics, that there would be a kind of physical dimension of the spiritual that makes the spiritual actually more a part of what we now conceive of as the physical universe? Something like the dark energy that seems to be around in space.
Well, first of all, let me say that there is a tendency among theologians, which I regret and speak against from time to time, to think that somehow energy is a more spiritual concept than matter. Now, of course, Einstein's equation E equals mc squared as much asserts the materiality of energy as it does the energetic character of matter. And I don't think that energy in itself is intrinsically spiritual. It seems to me that if there is any sort of straw in the wind in that direction, it is at the rationality end of it. It is the holistic, interconnected, beingless communion, if you like, end of it, which is more promising in that respect. And there, I think that potentially African thinking has a lot. I would have guessed would have a lot to contribute to it. I mean, Western society is immensely atomized. I mean, it's our anthropology is absolutely the anthropology of the individual self. Doing it my way is human fulfillment, and so on and so on. I mean, I don't want to endlessly prophesy against the present days, but I mean, there's no doubt that we are very much caught up in that. And even during my lifetime, I can see how that has changed social thinking in Britain in a sort of way. Now, at least in some parts, presumably tribal Africa, there's a much stronger recognition and experience of communality, of interconnectivity. And I think that could be a very powerful and necessary corrective to Western thinking. Going back to the question of intelligibility, I want to say this. I'm not exactly sure I have this or what I've just said, but one of my favourite quotes, these occasions are occasions for favourite quotes, is from Bernard Lonergan. Bernard Lonergan says, about page 650 in Insight, God is the all-sufficient explanation, the eternal rapture glimpsed in every Archimedean cry of Eureka. Now, I love that quotation, and it speaks both to the scientist in me and to the religious believer in me. And it's connected with this question of intelligibility. The deepest intelligibility is a theistic understanding. And the deepest form of theistic understanding, I think, is Trinitarian theology.
Thank you, Professor. If I could put one in at this
Yeah.
stage. It's very interesting what you said about relationality and how that reflects the Trinity. I suppose one could go down that road a little bit further. There's always a danger of ending up in tower physics territory. We try and make too strong connections, I suppose. But say, theological concepts such as perichoresis.
Yeah.
Would you want to say anything about that?
Well, yeah. Well, yes. I mean, there are analogies on there. I mean, theology, of course, has an impossible task. I mean, everybody who thinks about it for 5 minutes recognizes that finite human beings will never have the adequate resources to speak about the infinite reality of God. That, of course, is mitigated by, we believe, God's acts of self-disclosure, particularly in the life, death, and resurrection of Jesus Christ, so that God makes accessible to us things that are accessible to our understanding. But I think that I mean, I wrote that little book, Science and the Trinity, to try and explore that a little bit. I mean, it is very striking that the Trinitarian theology sees the being of God as, in some sense, constituted by that perichoretic exchange. Now, perichoresis is a sort of interpenetration of the persons of the Trinity, of a kind that we don't have. I mean, it's part of, I mean, go back, you see, there's very interesting problems there. I was saying earlier that initially physics started all atomistically, and the problem is how do things get connected, and field theory eventually was invented to help that. Now, because of the entanglement and stuff, we're on more tending to ask the question, how has it come about that there are isolatable circumstances, which of course is necessary for experiment, obviously, and so on. So the problem has got turned around that way. Similarly, Trinitarian theology has always been trying to steer a course between two unacceptable extremes. One unacceptable extreme is modalism, which simply says the three persons are just different aspects of God encountered in different circumstances. That's not enough. Equally, of course, tritheism, there's three gods in a fairly amicable relationship with each other. That isn't the Trinitarian picture. The way to try and square the circle in that respect has been this notion of perichoresis, that the three persons of the Trinity interpenetrate each other in a way that's not possible for us. But of course, all forms of relationship depend upon both separation and connection. Relationship isn't just being swallowed by the other. So I mean, you have to have, you know, if you have A and B in a relationship between them, you have to have A and B in their separateness, but the relationship means that they're not a separate thing. And it's credible, it seems to me, though of course hard to understand, that the intimate relationship of the Trinity is of course is different, but there is some faint analogy between really close human relationships. There are people with whom we are pretty close, so they always remain a mystery to us. Even those who are nearest and dearest to us remain in many genuine respects a mystery to us, and that's part of the rewards of the relationship too. But in the Trinity, in fact, it isn't quite that way.
Thank you, that's very helpful. Bill, do you want to?
Well, I've had a lot to say this morning, but someone else will.
Well, we've got time for both of you.
Well, I'd just like to push you a little bit, John, on the issue of emergence and downward causality.
Right.
So you kind of implied in your, I mean, I share, as a scientist, I share your queasiness about jumping too readily on the downward causality bandwagon. On the other hand, I'm genuinely uncertain what I think about this whole business of, you know, whether there are simple forms of emergence that are all bottom-up causality, and then there are more complicated ones where we might be able to think about downward causality. And for example, here's the way this comes into relief, and since you're a physicist, I'd like to know the way you think about this. In principle, if we were smart enough and we had enough information processing ability, we could write a Schrodinger wave equation that would predict the motion of probabilistically predict the motion of every atom in this room over the next 10 minutes. In principle, we could do that. Now, that would be a complete description of the physical system that is this room in one sense, and all the causality is bottom up. And yet, that Schrodinger wave equation and the prediction involving the motions of atoms would know nothing about persons in this room. They would know nothing about feelings of curiosity that motivate us to be here. They would know nothing about, you know, hunger that's going to take us out of this room in a while. And so, you know, so in one sense, it's a complete bottom-up description. We could say, well, emergence is all bottom-up, causality is all bottom-up, and the gap is just epistemological, you know, like your water example. But where, I mean, at what point does emergence, would you say, you can legitimately consider the notion of downward causality, and where can't you? And if there is downward causality operating in the room, how does it coexist with the upward causality, the Schrodinger wave equation?
Well, I mean, that's a very interesting question. I'll make a couple of comments. First of all, the motion of the atoms of air in this room is not as simple as it looks. Actually, as far as intermolecular collisions are concerned, you can treat them essentially as billiard balls. And it's a very simple calculation to show that, in fact, even on a tiny fraction of a second, less than a microsecond, the question of whether this particular atom is going that way or this way will be incorrectly calculated if I have failed to take into account the existence of an electron, the smallest particle of matter, on the other side of the observable universe, about as far away as you can get, interacting with the area through gravity, the weakest of the forces of nature. So, when you look at things in detail, there's an incredible degree of interdependence. I don't talk about that particular form of relationship this morning, but it's there in that sort of sense. That's the one thing. The other thing is this question of what's the status of the laws of physics. I mean, I think that I think that what we call the laws of physics, particularly of fundamental physics, are in fact themselves emergent. I think they are downward emergent approximations to a much more subtle and complex reality. They're emergent in the approximation that, you see, the laws of physics have been very well verified, time and again, but only in a very special set of circumstances, essentially isolatable circumstances, because you can't do experiments unless you maybe exclude the background. So I think that the Schrödinger equation and all that sort of stuff is an approximation to a more subtle and simple reality. Of course, I have not the slightest idea what that reality, how to describe that reality, but I think we have no reason to say that you see, there's a tremendous bias in all our minds. I talk about fundamental physics. I'm talking about subatomic physics of elementary particles, but we all think it's fundamental physics because somewhere or other the constituent character of it seems to make it more important. I think that my dear friend Arthur Peacock, who many of you know about, who died just recently, used to like to say electrons and things are not more real than molecules, than cells, than persons, and I think that's right. I think that we have no real notion of how to talk about the causal structure of the world. We have clues to it. We have regimes in which we have very good grips on it. But those regimes are limited and not exclusive. So that's why I try and answer that question. But I would emphasize that I do think that if you are going to talk about downward rotation, you have to at least tentatively, obviously, conjecturally identify where there might be that causal room for manoeuvre for that top-down effect to genuinely affect things. And I say the Kaufman model shows you that it's harder to think straight about these than you might otherwise have thought. But
Thank you.
that's how pre-Socratic planes around. Yeah.
Was there a question over here? Was there a question?
They're all too
I'll
hungry.
throw another one.
They're all too hungry.
You talked quite a bit about quantum theory,
Yeah.
and yes, this is
Yeah.
a generally accepted view that it's ontologically indeterminate.
Right.
But is quantum theory still incomplete in the sense that it does throw up these pretty weird paradoxes? Schrödinger's cat.
Yeah.
Is the cat alive or
Yeah.
dead? When
No,
is it?
that's really a problem. Yes, no, that's very true. Yes. Well, yes. I mean, the big paradox about quantum theory is that though it's been around now for whatever it is, more than 80 years, and immensely successful, but we still don't really understand it. And in particular, we don't understand how the fitful quantum world relates to the reliable everyday world of, for example, laboratory measuring apparatus. This is the measurement problem in quantum theory. I have a state where the electron is here, a mixture of here and there. I make a measurement to find out where it is. Each time, I will get a definite answer. It's here, it's there. I won't get the same answer every time. I can calculate the probabilities very, very accurately. But what actually causes me to get an answer here on this occasion? Nobody knows. There are lots of suggestions. None of them are really satisfactory. And so that's another example of our incomplete connectivity in the causal structure of the world. And when you think of the role that measurement plays in science, I mean, we don't understand how measurements play. It's really humbling, I have to say. So there are incomplete things about quantum theory in that sense. That's a very great paradox of it. And then Schrödinger's cat is another thing. I mean, it's inconceivable that the cat doesn't know whether it's alive or dead. But then where does it stop? I mean, if it was a worm in the box, would the worm know whether it was alive or dead? Well, it wouldn't know in the self-conscious sense, obviously, but presumably it would be either alive or dead. I mean, they're just not. That's a very, very good example of how we just don't know
how the different levels of the world relate to each other. We really can't put them together. Even in physics, which I thought was an easy subject compared to biology.
And is consciousness doing something, or is it measuring apparatus?
Well, there are people, seriously, very, very distinguished scientists. I mean, Figner was one of them, who thinks that consciousness will produce stuff. But, I mean, are we to believe, I mean, consciousness is pretty low rival on the cosmic scene. I mean, are we to think there was no quantum event ever had a determined outcome until, I don't know, Homo erectus or somebody came along? It doesn't seem very likely, really. Are we to believe that if I set up an experiment which produces a computerized printout, which is stored away unseen in a drawer, but until I open that drawer 6 months later, there is no definite imprint on the paper? Well, it's possible, but it's not very persuasive.
Well, it shows the weird world that,
It is the weird world. It is the weird world. I mean, our great temptation for all of us in different ways is the Procrustean technique of chopping down the complexity and puzzling character of reality to make it something manageable that will fit into the bed of our chosen understanding. And we really have to fight against that.
Good, thank you. Dennis.
Yeah, can we just come to Trinitarian theology and entanglement and so on? And I'm a great believer also in the language of consistent with, because I think it's the language we will use as scientists and so forth. So yes, clearly non-locality and entanglement is consistent with the Trinitarian concept of the universe and so on. But in a sense, I find that, I mean, it is quite an abstract, kind of concept in a way. It's about particles and about things being connected on the other side of the universe. But it seems to me, in a sense, and this is the biologist coming through, that it's the existence of personhood, the actual existence. I mean, that seems to be far more mysterious, in some sense, in a way. And I just wondered whether the entanglement really was that. I mean, couldn't it be consistent with a lot of things that are not Trinitarian at all?
Well, there's certainly no entanglement. I mean, it could just be a brute fact about the world. That's the way quantum theory happens to be. That's it. I mean, I wanted myself to have as integrated a view of the world. I want such understandings that I have the different levels to be as constant as possible with each other. So that's one thing. Now, of course, I've been talking to physicists this morning, and that's a very limited point of view. And so I'm a sort of peddler coming along and I'm packing my wares and spreading them out. And I agree that I think that the existence of persons in the universe is probably the most astonishing thing that's happened in the whole history of the universe, the self-conscious being. Pascal said, human beings are just reeds. I mean, we're tiny insubstantial things in this vast, vast universe. But we are thinking reeds. And that makes us greater than all the stars. Because we know them and ourselves, and they know nothing. And I think the most astonishing thing that's happened in the history of the universe is the coming to be of persons. And therefore it is very suggestive, as you say, that personhood is a very, very key category in understanding reality. It's not a category that physicists have anything to say about. As people, of course, they have a lot of experience of it. So, yeah, I agree, but I mean, I've only had a limited objective this morning.
Can I have another consistent with
The question at the back.
I mean, as physicists, I wonder if basically what we're doing is absolutely desperate to unify everything, both our religious experiences and our scientific experiences. I mean, basically, are we not doing any more, I wonder, than simply saying, well, okay, we unified electricity in electroweak theory and so on. I mean, I don't think, like you, we come from the same sort of background, but I just wonder at the end of it, what exactly we have actually achieved. We've done a wonderful effort of unification, and I'm quite happy about that, and I'm pleased to have done it. But have we actually done anything more than that at the end of it?
Well, that's a very interesting question. I mean, I think there is an instinctive drive among scientists to seek unified understanding, and physics, of course, again, because it's easy and has been pretty successful. I mean, I think at the moment physicists are rather thrashing around in trying to find a grand unified theory that and so on. And I think some ideas are missing that only the nudge of experiment will push people to discover. But there is this other, and it's again fundamental, like so many other instinctive feelings that seem to me support science and fuel science. It seems to me that whether perceived as it or not, it is in a sense a religious
desire or religious belief or commitment, the world makes sense, and it makes total sense. And talking about the world as creation, one of the things I implied is that the world is a creation, is a cosmos, not a chaos. And therefore I think that instinctive drive towards unification at the banal level of physics is the right instinct in relation to the world. And basically is a veiled form of religious instinct. This is the experience of wonder, which is very fundamental to the reward for all the weirdness of doing science, is again, I think, a veiled religious experience. I mean, lots of scientists will want to speak about that. I think it's fundamentally a worshipful experience. Not all my friends will see it that way, but I think that's what it is.
I think it's very interesting. I've been in India recently, and it's very, very interesting talking to Hindus picking on this. And then I think that was broadening my own experience. And then actually going and watching dances in southern India, and you say, well, how can I sort of have a unified Western science with our Western and Eastern theology? Now I was faced with the task of, do I seek to unify this with Hindu understandings, both of dance and of their polytheistic ways as well? What exactly am I doing there?
I actually think that after suffering, the most urgent theological problem, and it will be a problem for the third millennium, is to begin to understand how the world's basic religions relate to each other. I mean, it's not the question that we know everything, they know nothing. It's not a question we're all saying the same thing, but in different culture and different languages. That's not true either. There's a great complexity there, and I mean, it's going to be a long, hard, and painful road to hoe.
Yes, this is an important issue. Thank you. Stephen, you have a question?
I was just going to comment on the idea of the search for unity, unify things, and that being a characteristic of the Trinity, which does in a way, perhaps, it's more evidence of
yes. I mean, the Trinitarian theology is. I mean, again, it's the balance, isn't it? I'm very Anglican thought. It's the balance between unification and the acknowledgement of diversity. I mean, that was obviously an acute theological problem in relation to the Trinity. People felt that they had these identifiably different encounters with divine reality, not just perspectively different, but different in their intrinsic character. But nevertheless, they couldn't give up the belief of the Lord our God is one Lord. And of course, in the New Testament, people are just sort of, I mean, they're so seized by their experience of Christ that they're saying all these strange things about the Lordship of Christ and so on, without being able to stop and think of how that relates to the Lordship of the God of Israel. That leads eventually to Nicaea and Chelsea.
Right. Approaching lunchtime. Maybe one. Okay, Bill, give you the final.
John, taking advantage of physicists, you as a physicist, maybe Rodney would want to comment too. You made a comment in there about chaos being intrinsically, reflecting intrinsic unpredictability in the universe. And then you use the same language about quantum mechanics. I know some of us who are not physicists are probably a little confused about that, because on the one hand, I hear language sometimes like that about chaos. And sometimes I hear, no, chaos is just Newtonian, but with the lack of ability to specify initial conditions enough. So is chaos, when you use intrinsically indeterministic or probabilistic, do you mean the same thing as quantum mechanics, or is there something really different here going on?
Well, that's a very, very, very good question. Absolutely. I've had a long battle about all this. For years, people kept on drawing me aside. I mean, physical science friends drawing me aside and telling me that Newtonian equations are deterministic equations, which I didn't know actually. The point is, we know that they're not the exact equations. And again, they are, I think, we're back to this question of approximation to the richness and subtlety of reality. As I say, we know that very soon the degree of accuracy with which you'd have to know the initial conditions is actually forbidden by quantum theory. But we can't put the two theories together because they don't fit on each other. So they're just unresolved problems. So of course it's true. I mean, chaos theory arose from the study of the properties of deterministic Newtonian equation. It started with Poincaré actually, and wasn't properly recognised at that time. But we now know those equations are not the true equations of the world. There are very good approximations to it, and that means that we are free to defend the state and defend a metaphysical interpretation of it. So just saying deterministic chaos is adopting a point of view. It's a possible point of view to take. It's possible in the end of the quantum theory problem, but you can take it to some extent. But you're not driven to do that. We have to take very seriously that fundamental physics is not as certain or comprehensive in its knowledge as often we like to.
Freeman Dyson makes that point, right?
Oh, yeah, well,
that matter is strange stuff.
Yeah.
There's plenty of room here.
Yeah, I just hear him make that point. Yes, yes.
Well, I think that's a wonderful point to stop. Thank you, John, for a superb talk.